All right. So we're going to start this, maybe not where you guys think. Okay. We're going to start off talking a little bit about something called fatigue. And then the fatigue will hopefully set the stage for how we need to train. Okay. Because in a lot of instances, the induction of fatigue, okay, doing more than what you are accustomed, generates fatigue, and then it's the changes in physiology that tend to accompany the fatigue, okay, or the prolonged exposure to those things that are going to potentially drive the actual adaptation. Okay. So by the end of all of this, you should have a general sense of how you should train. Hopefully you'll figure out how everything gets completely overcomplicated in my mind. You'll know what it is that changes, and you'll have some sense of what the stimulus is that's driving some of these things. Okay. So before we talk about fatigue, I want to do really, really big picture on aerobic training. Okay. Most people, if we ask them the question, why do we train? They're going to come at this from sort of two answers. Okay. One of them is, I want to increase my exercise performance. I want to be a better endurance athlete, whatever that might look like. Okay. Whatever that might look like. You might just simply want to be able to run a 5K because you've never run a 5K. Or you may want to run a marathon under 3 hours, whatever it is. You want to qualify to go run a Boston or something, whatever that might be. Okay. So these increases in this kind of distance performance are mostly people are going to talk about, I want my VO2 max to go up and I want to change my lactate threshold. Okay. Now there's a couple of additional parameters that we should probably throw in here, something called critical power. It's going to play a role. We can talk about movement autonomy that are all going to also play a role in the midst of some of this. But these are the primary things that people think. Okay. When you get to be my age, or maybe a little bit younger, or hopefully for some of you guys older than me, the only real thing that I'm ever trying to train for is probably to increase health. I have to run so I can eat. Okay. I gotta run so I can eat, and then I have to buy new pants. Like that's the real kind of, that's as deep as the whole thing goes. And then now that I have a toddler, you'd be amazed at how freaking much they run around. I need to go like chase her around. So having to carry her for almost 3 years now, like has jacked up my back and things. And she weighs like almost 40 pounds now. So she's gonna be a tall lady at some point. But people are talking about increasing. Okay. We'll talk a little bit about the health thing, because some of the stuff that increases VO2 max is going to increase health. Although to be 100% honest, if we had to pick a measure, as I tell my undergrads, if you had to pick something to figure out how healthy somebody is, just guess their VO2 max. It predicts their mortality. People with higher VO2 max live longer. In the discussion, done. We got NIH funding in my PhD lab by saying basically exactly that. Right? These people with spinal cord injuries, they don't ever move around. They get every disease you can think of before regular people. Their VO2 max is super low. We're going to try to train and make their VO2 max go up. That will make them live longer. Plot VO2, all the data from the Cooper Clinic in Dallas, VO2 max against mortality, it predicts. So this is going to kind of go into this. We're going to really focus much more so on kind of performance. So to that end, what is it that limits performance? Okay. If we're going to have a race between Cy and Josiah, what's going to limit who wins or who can run the longest? Okay. The idea behind that is it's probably going to be something that we call very, very loosely fatigue. Okay. We will define what fatigue is and its location and causes in the coming slides, but this is the general thing. Okay. Right. If we said Gabe's going to do a wall sit and he's going to do wall sits against Brady, who wins? Who can do it the longest? It's whoever doesn't fatigue as fast. Okay. So if the thing that limits performance is fatigue, if we want to make performance go up, we need to understand the things that cause fatigue so we can try to alter or change those things, thus limiting fatigue and then hopefully increasing performance. Does that idea make sense? Okay. Does that idea make sense? Okay. I had some undergrads this morning that I gave them the Fick equation, and I told them they needed to know for their test on Monday, they needed to understand the relationship between the various parameters of the Fick equation and things. And they looked at me like I was growing a third arm. And I was like, well, so what happens if I make the cardiac output go up? What's going to happen to your VO2? They were like, what the fuck is this? I don't understand. And it just occurred that they don't get to do that very often. They don't get a lot of integrated physiology. So I just want to kind of believe from, if this causes this and this limits this, and if I can prevent it, that should get better. Okay, that should get better. So we need to understand the causes of fatigue, which we'll spend multiple slides doing here in just a minute. Okay, so as you will see with this, there may be various locations. And those locations are going to exist maybe within the muscle. They may be within your sort of metabolic system, your metabolic machinery, some of which are all of which are actually in the muscle, right? It may be something on the cardiovascular system or the respiratory system side that are going to then affect the metabolism and affect the muscle. It really all kind of comes back to the muscle. But depending upon what it is that's causing fatigue, okay, then these sorts of things, if we get changes in these particular systems, that may limit fatigue and therefore limit our having to stop during exercise. All right, so let's talk about fatigue. Let's talk about fatigue. One of my favorite things, okay? Muscles, probably my favorite, fatigue, probably my second favorite kind of thing, but it's really kind of all tied in with muscle. Fatigue is defined generally in the exercise physiology literature by a British fellow, his name was John Edwards. It's published in like 1979 as a failure to maintain the required or expected force. Okay, what this means, okay, what this means is that you're trying to produce a certain amount of force and you can't. Okay, or you were producing that force a second ago and now you're trying and you can't. Okay, this is different from what we would call weakness. Okay, weakness is an inability to develop an adequate amount of initial force. So if I was to come over and try to pick Brady and his desk up and I couldn't do it, okay, that would not be fatigue, that would be weakness, because I can't do it at all. But if I can do it once and then a second time, but then I go for a third rep and I can't do it, that's fatigue, because I could do it, now I can't. Okay. Do you all understand that particular distinction? I think it's really important. Okay. So in other instances as well, we're not going to cover much of this in class, okay? But there's also this idea of how fatigue is different than what we would call an injury or a muscle injury. Okay? You guys ever been sore? Have you had muscle soreness? Something like that? Yes. Okay. Sarah, when was the last time you were sore? Yesterday. All the time, okay? Well, they're probably overtrained, would be my guess. But if you're sore, you probably have muscle damage. Okay? When you have muscle damage, you have physically messed up your sarcomeres. You physically messed up the ability of actin and myosin to interact. And so you may not be able to develop enough starting force, or if you can, you may lose some of that force faster than you would under other circumstances. Okay? So from a purely force outcome perspective, injury may look like fatigue, but they are going to be caused by very different mechanisms. Okay? By very different mechanisms. One of the things that we're going to talk about with fatigue is recovery from it. This has become a really, really, really big deal, okay, in the world of sports science. Okay? We forgot for the longest time that maybe letting people rest and have a day off or an easier day might actually benefit them. Okay? Because sometimes you may have fatigue that lasts for days. Okay? It may last for days. Other kinds of fatigue may last for a few seconds. It just depends. It depends on what's causing it and where it's coming from. Okay, so we will get into all of this. So that's one of the ideas that's different. Fatigue and injury are different in that. A lot of times the forced depression from fatigue may only last a few minutes, a few seconds, a few minutes, whereas injury, if you've got muscle damage, you may have those symptoms for a week or 2 weeks, or if you're in some of our crazier studies, like 3 weeks, and you're still not all the way back to the initial start. Okay. That's kind of what's going on. We tend to group fatigue into two very broad categories. Okay? Central fatigue and peripheral fatigue. The outcome is the same, an inability to produce the desired or expected force. But what central and peripheral tells us is where's it coming from, right? Where is the physiology getting messed up? Peripheral fatigue is a failure of the motor neuron, the level of the motor neuron, or the muscle to function properly. Okay? So it may be action potential propagation from the motor neuron into the axon, all the way from there, sort of distal out to the cross bridge. Okay? Some people debate about, do you include the motor neuron in the central side, or do you include, is it actually start at the axon versus the motor neuron? It really doesn't matter that much. Okay? Central fatigue, okay, is a psychological factor, something like motivation, pain, sense of that effort that serves to limit force production. It tends to involve descending motor pathways, so motor cortex, down the spinal cord, whatever signal we're trying to send to the motor neuron. Okay? Central fatigue, okay, plays a very big role in long duration exercise. Central fatigue, when you get too hot from being able to, from exercising outside when it's hot, that's mostly central fatigue. Okay, so when you deplete all of your muscle glycogen or your blood glucose, that's going to cause central fatigue. There are people that argue that central fatigue is the major cause for fatigue in our daily lives. There's a real persnickety MD from South Africa that argues that all fatigue is central and none of it is peripheral. He's totally full of shit. That's not true, right? We induced peripheral fatigue in my lab like an hour, right? Like I promise you, this can happen. But the argument, his argument is, have any of you ever exercised until your muscle couldn't relax, until you essentially reached rigor? Ethan, you're saying you have? Okay. So Ethan's experienced peripheral fatigue in his everyday life. Okay, the rest of you were just wimps and you stopped. It was uncomfortable, you didn't like it, you could have done more, but you didn't. Okay, that's the argument behind central fatigue. Is think about all the times you stop exercising or you stop doing something, and imagine if I'm sitting behind you with a cattle prod, if you could you do one more rep? Could you do 2 more steps of distance on your run? Could you have pedaled at a slightly higher power output on the bike for a very, very brief amount of time? If the answer is yes, that's central fatigue. Okay, that's central fatigue. You could do more, but you're choosing not to. It's very, very common. Okay, it's very common. So I would argue if you've ever done reps to failure lifting weights, then at some point you're peripherally fatigued because you're probably trying and that weight didn't go anywhere. Right? You're like, I got this, I'm not going to know. That's peripheral fatigue. Okay. So we'll talk very briefly about how do we measure these kinds of things and kind of what are some of the common limitations that are going to be there. And then that will lead us into accumulating a certain amount of peripheral fatigue. Lends itself to the induction of central fatigue. Okay. So there's an interaction between these two things. When you go run, and it feels painful and it feels uncomfortable and you don't like it and your muscles and they're burning, that's an accumulation of peripheral metabolites that are sending signals back to your central nervous system, be like, hey, we don't like this. Slow down. There's an interaction. Some amount of either of these two things that we think is responsible for driving the adaptations, making more mitochondria. Where do you have a question?
So whenever I helped Dr. Pereira with his group test thing, whenever I just like couldn't do, like it just kind of like stopped. That was peripheral fatigue. It just kind of like I didn't feel like I was doing anything else anymore. It's just like,
I mean, were you trying as hard as you could?
I couldn't do anything else. It was just,
Then, yeah, I assure you that during all of that, there is peripheral fatigue that's happening.
Yeah.
Whether that was the exact thing that made you stop or if it was some combination of those two things. A lot of exercises, I mean, unless we do it artificially like what we did in my lab today, then there's going to be both that are happening. Okay. So, and I apologize that this and this are not going to be exactly the same thing. So they were taken from different things, and I need to reconcile them. So generally, we think that peripheral fatigue is due to an intramuscular mechanism. Okay, we generally think of this as being something on the muscle side of the neuromuscular junction. That's not 100% true. Okay, if there's a failure of action potential transmission in the axon, okay, that can be considered peripheral fatigue. It's not very likely. Okay? It's not very likely in sort of voluntary human exercise, but it's possible. Okay? So it is difficult to measure and quantify peripheral fatigue in humans because I can't see into your muscle fibers very easily. Okay, so one of the ways that we try to understand and explain what is happening is we can use electrical stimulation of, let's just say, the motor axon. Okay? So let's say I want to do a gripping exercise, like what Brady was doing for Dr. Correa. I could put electrodes right here over your ulnar collateral nerve, and I could zap that nerve. That's just a collection of axon bundles, right? I can do that, and it makes everything downstream of it contract. So I stim the nerve, and your muscle goes without you ever having to tell it that it's going to go. So when we do that, what we see is, as peripheral fatigue occurs, because there's no central component whatsoever, we see a decrease in the twitch amplitude, so force production falls. Okay. We see if we ask you to squeeze as hard as you can after having done this, maximal force goes down. We see a decrease in power. We see a decrease in the rate of tension development, which tells us, right, that if this rate of tension development is going to be mostly dependent upon sort of calcium release and myosin ATPase function, that obviously this peripheral fatigue is having some effect on those things. So here you can see, and this is more of, I don't know what I'm trying to show you guys. So this is sort of a strange, I don't know why this is here, but I'll explain this. These are some data from a study that we published a few years ago. And I'll explain what this is. It's a little bit of a unique sort of situation. Okay. One of the things to understand about fatigue and how we sort of look at fatigue is it can manifest itself in multiple ways. Okay. If I told Sarah she had to get up and she had to jump as high as she could over and over, it seems pretty pertinent to what maybe she does with her sport. We just repeat it. Max jump, max jump, max jump, max jump. She's supposedly, right, she's trying as hard as she can, as hard as she's able to. Right? But what if I said, no, don't do that. What I want you to do is you're going to sit on the wall. I can do this. You just have to hold yourself. This is obviously not maximal, right? Because I'm able to sit here for some period of time. Okay. As I sit here with a sub-maximal contraction that I'm going to do for a prolonged period of time, right? What you guys see, this is being graphed here in the bottom in these triangle things. You'll see this is force production, okay? At 25% of maximal force being held constant. And then what you see in the other two, this is the surface electromyogram signal. So this is a measure of the electricity going through the axons and the muscles and the sarcolemma. And so what you will note is that this is at the start. This is all the way at the end. Okay. This is going to show us it starts off doing one thing, force is constant, and then the EMG signal is getting bigger. So what this tells us is that the brain is having to send more and more signals to generate this exact same force. So the brain and the central nervous system is having to work harder. Okay. So then we get out here to the end and we have to stop, right? And this is going on. And so is that due to sort of a failure on this end? Probably not. Is it due to that it's just comfortable and you can't kind of some peripheral things are happening? So I just want to make that distinction between maximal things done over and over again versus a submaximal thing, because they're both fatigue. So one of the ways that we can try to assess how the central nervous system is working, and whether we're experiencing central fatigue, is using a technique called twitch interpolation. Right? And so the students in my lab haven't seen this yet, but we talked about it. So imagine this particular scenario. Okay, I'm sitting and I'm doing knee extension. Okay, knee extension exercise like so. It's isometric, so I kick as hard as I can and I hold it. Now imagine that we've got an electrode over my femoral nerve. Okay, and what we're going to do is while I'm kicking as hard as I can, we're going to zap my femoral nerve with a large amount of electricity to generate sort of one big action potential. Okay, so we are interpolating a electrostimulated twitch on top of my voluntary contraction. That's what is happening here. And so what you will note is the person kicks, we're going to get some force, then we hit them with the stem, and we get this little tiny little bump of extra force on it. So what that tells us basically is that if we are having you do a maximal contraction and we give you a superimposed twitch and we get more force, that means that you were unable all by yourself to recruit all of the motor units that are going to that particular muscle. And so we look at the size of this twitch, and then after you've relaxed out here afterwards, we give you another twitch while you're not. And we look at the size basically of the superimposed one to what it ought to have been, okay? And we can calculate from all of that basically how much of the resting twitch you kicking voluntarily makes go away. And so from that, we can calculate something that people call motor unit recruitment or motor unit activation. They get surprisingly fussy about whatever that is, but that's a way that we can do all of this. And what we can see is this is from a study where they had people do from like 20 kilograms of force up to almost 120 kilograms. So this is just a very light load up to a near maximal load, and they're doing the interpolated twitch on them. And what you can see is the size, or this is the ratio of the superimposed doublet to their potentiated doublet. So this is just showing this force goes up. You get more and more force. The size of the superimposed twitch is going to get smaller. And that's kind of how we're going to try to quantify motor unit activation. So this is a measure of central fatigue. Okay. But if we look at what happens after you've done something for a while, we can look at what happens to the resting twitch. We can look at the twitch characteristics. We can look at rise time. We can look at relaxation time and all of this, and learn stuff also about peripheral fatigue. So these are going to be things that we can do. Another way to try to get at the central side of things, people do something called a central activation ratio. This is basically the same thing, but rather than giving a person a twitch, you put electrodes on the surface of a muscle and you zap them at like 100 hertz for a couple of seconds while they're kicking. This is excruciating. It is unpleasant. The other one, you get a lot more stim, but it's on for like a millisecond. And so it's almost over before you even know what's going on. This shit hurts real bad. And most people can't take enough electricity to make this sort of maximum. So this is kind of falling out of favor, but it might be something you would encounter. But again, a way for us to try to quantify what's going on from a motor unit recruitment standpoint. Okay. So if we look at where peripheral fatigue can take place, there's going to be several sort of primary locations. Okay. The first of them is action potential propagation on the motor axon. Okay. This is sometimes called an axon branch block, and what is going to happen is that the axon itself is going to become less excitable. We see this at times in animal models of fatigue. We don't see it very often in humans. We can look at trying to do needle EMG electrodes and try to hit them right on a motor axon and try to see if we're getting a slowed or a decrease in propagation. That's kind of messy to try to do, but it can in theory be done. It requires really, really high and prolonged high frequency stimulation. Okay. This is one of those things that it's a theoretical phenomenon that can occur. We can observe it in the laboratory, but Ethan goes to work out today. He's probably not going to be able to induce action potential propagation failure in motor axons. It's possible. We can all agree that probably, I'm sure Ethan works out really hard. He's a beast, but probably not getting this. Okay. Additionally, okay, and it's also going to be something that's not going to be seen super duper often. Could be a failure of neuromuscular transmission. So there would be a decrease in release of acetylcholine across the neuromuscular junction. Okay, so we may see a decrease in vesicle number and the amount of acetylcholine in the vesicles. All right, this is from a failure to be able to reuptake the acetylcholine back into the nervous system side quickly enough. Okay, and it may also be due to a similar kind of thing like the action potential, that there could be an impairment of the voltage-gated calcium channels, initiator of releasing the vesicles. Okay, we see this as well occasionally in kind of animal or in vitro kind of isolated muscle preps where you may get a desensitization of these acetylcholine receptors on the muscle side. Again, this is really, really rare. It's hard for us to ever be able to kind of see or understand this in voluntary human exercise. If you want to come to my lab, we will invite everybody very soon. We'll do an E-stim protocol where we can maybe see some of this with our E-stim protocol because we hit the same axons and the same muscle fibers over and over and over and over again repeatedly for like 5 minutes. And so in that instance, maybe we can get a little bit of this. That's a very unphysiological in some ways. Okay. So here's a situation where we think we are seeing depletion. And so this is a graph showing in the solid, okay, in the solid circles, we're stimulating the muscle. So I put electrodes on your quad, on the outside of your muscles, okay, on your skin. Then in the open circles, and I have no idea how people manage to do this, they're stimming the nerve. So it's in the quad, but I'm going to stim the femoral nerve. What we see from all of this is that when we stim the nerve, okay, we can be more certain that all of our firing sort of action potentials are going to get transmitted across the neuromuscular junction into the muscle. We see greater fatigue with nerve stimulation versus stimulating the muscle itself. You see greater fatigue at 75 hertz versus 40 hertz. So this will very clearly indicate a failure of neuromuscular transmission. We've got to stim the nerve, which I can promise you that what these people did in this thing, no one wants to do. Like, I don't know how they got people to do this. This is wild. So we tried some of this in my lab a few years ago, and I was basically crying. Like I physically ripped the electrodes off, but I always get it stiff. I was just like, make it fucking stop. So it's really bad. Really, really unpleasant to do that. The nerve or the muscle side thing is not so bad. If you have questions, Lisa's had it done. I do it a bunch. Chris has had it done. It's not so bad. I mean, we can make it bad, but it's not done so bad. Okay. So if those are kind of uncommon sites of peripheral fatigue, especially in humans, what are the common sites? Probably the most common is going to be a failure of excitation contraction. Okay. So a failure to signal in the T tubules, you're going to accumulate potassium ions in the interstitial space. They're not going to be able to get put back in onto the inside, and that's going to reduce the membrane side of the T-tubules because they're so small and they're so narrow. It's hard for us to have enough sodium potassium pumps to repolarize. And either in conjunction with this, so it would be a consequence of the T-tubule being decreased excitability, or at other times with it. So it's not caused by the T-tubule failure to depolarize. It's going to be caused by a separate thing, is a failure to release calcium from the sarcoplasmic reticulum. So as intracellular ADP goes up, which happens during exercise, you will actually get some calcium that will bind onto the ADP, and it will bind on magnesium, and then that's going to begin to inhibit the ryanodine receptor. So ryanodine doesn't work as much. There's going to be communication between the DHP and the ryanodine receptor that gets messed up. You may have inorganic phosphate that actually flows from the cytoplasm into the sarcoplasmic reticulum. It binds with calcium, and then the calcium can't get released that way. And you may be unable to pump a sufficient amount of calcium back in, so there's going to be a failure of the calcium ATPase to be able to pump it. The general thing that drives all of this is a decrease in pH. It's an increase in hydrogen ion. But these two things collectively tend to be the most common cause of peripheral fatigue that we see during exercise. So don't worry about muscle wisdom. This is a weird thing that I don't really want to talk about. Okay, so we talked about central fatigue a little before. We defined it, right? Generally, it's the spinal cord and above. People will sometimes refer to central fatigue as being a failure of what we call central drive or central command. So in order to test that you've got central fatigue, you have to do voluntary exercise. Okay? I would just say that any exercise-induced reduction in maximal voluntary force output, okay? If you're trying to do something and your nervous system won't let you, in this instance, that's going to be okay. So as we've already mentioned, it may be from reduced signaling. It may be due from, let me back up. Okay, sorry. Reduced signaling to the muscle from brain or motor neurons. This is the thing. Okay, this is what happens with central fatigue. This is it right here. Okay? What may happen is that afferent feedback from muscles, things that sense pain or discomfort or exertion, will signal back into the brain, and then the brain reduces the signal to the muscle. Okay? So afferent feedback leads to this. Substrate depletion, so a lack of glucose or muscle glycogen, is sensed in the brain and leads to reduced signals to the neurons. Or an increase in core body temperature, which you guessed it, is sensed in the brain and leads to a reduction in the signals from the brain. So,
what about like if people have conditions that like have like MS, people with cancer, do they get more peripheral or?
it depends upon what we're asking them to do, and that's what how severe their symptoms are. So, I think if you have a stroke patient or you have somebody with MS, there may actually be, I mean, you could call it central fatigue, right? Because they've got some sort of a brain or upper spinal kind of spinal cord injury, or lack of myelin or something that's going to be there that's going to reduce the signaling, right, from the brain down the spinal cord to the muscle, or some inability in the motor cortex to make all of this fire. I mean, I would argue that's central fatigue, but it's not like, I mean, their muscle can do more than their central nervous system can probably allow them. But that may be a little bit different than kind of what we normally think of. They would have initial sort of central fatigue limiting their strength, right? Almost like you've got central fatigue that's causing weakness. And then once they start doing things, then this other stuff may happen. It can then further kind of feed in. And they have some sort of neurological pathology that prevents them from turning their muscles on to an extent that meets the actual size of that muscle and what the muscle all by itself should be able to do. Okay. So in some ways, that's really not central fatigue. It's a central version of peripheral fatigue, it's central pathology, as opposed to I could do this and then things begin to happen downstream and then the brain decides, let's shut this down. So I don't know, it would be interesting to see what Drew and Jordan had to say about this for stroke patients, or how their advisors define those kinds of things, because we can look at some of this by doing magnetic stimulation of the brain, and we can stimulate sort of right here, kind of at the base of the skull, as opposed to stimulating kind of downstream of the muscle, and really try to see where sort of in the central nervous system is that. Does that make sense? Mm-hmm. Good question. Okay, so this idea of substrate depletion, right? When your phosphocreatine is gone, what does that mean? Well, you can't get enough ATP, so you're going to accumulate hydrogen ions, and you just don't make enough ATP, and so you're not going to be able to recycle your cross bridges, so you're going to have to slow down. I would argue that phosphocreatine depletion will be this kind of peripheral fatigue. Glycogen depletion, both from the muscle and the liver, is much more of a central fatigue. So this happens during long duration exercise, or if you never eat carbs, which even if you never eat carbs, you're going to do some gluconeogenesis, you should have some. But what tends to happen is when your glycogen is gone, then you're going to try to maintain blood glucose levels with liver glycogen. And at that point, something weird happens where the brain begins to freak out and it gets worried that blood glucose will fall too far. And so the motor cortex is going to become less excitable, and so it's going to try to make you feel like you need to slow down. That's a little bit about fatigue. Okay. Questions about any of that stuff, guys?
Chris, we're talking weeks ago about environmental factors, how patients eat outside or
Are you talking about stress specifically?
Yeah.
So I think when we were talking about it, we were talking in regards to hydration and blood status. So can stuff play a role in fatigue? Just because if you're having to maintain our core body temperature, and we're using more energy to maintain that. So when we're in stress, our core temperature can go up to, 104, is when it reaches critical level.
Yeah, you get to about 40 degrees Celsius, and there are, in essence, temperature sensors in the brain. They monitor the temperature in the blood, and they're going to start increasing your excitability or cortex excitability. Stop doing what you're doing because you're generating all this heat in your muscles from exercise. And so they want you to stop, basically. One, so that you don't have to send blood flow to those muscles, that blood can go to your skin to dissipate heat, and you're going to stop making extra sort of internal heat. Because the gradient between what you're making versus outside has shrunk. If you care, they do some wild things. Again, in Scandinavia, by running arterial venous carotid catheters, and they infuse stuff at different temperatures, and they're measuring glucose levels and stuff, what's going into the brain and what's coming out, and monitoring the temperature of the blood going into the blood. It's wild stuff. And that's how we know a lot of this stuff related to the blood. If you assume running carotid catheters are safe, just put it that way. I'm not volunteering for that. Okay, any other questions? You need to get up and induce some fatigue for a minute. Anybody else wondering why? Is anybody else really hot? It was really fine here today. Did you think it's hot? Yeah. Okay. I'm just sweating something terrible here. So Okay. So fatigue is the enemy of exercise capacity. Okay, but it may, as it turns out, be one of the primary things that drives the adaptations that take place with aerobic training. Okay, and it's not so much that it's the how hard you have to make all of your systems work to get to that place where fatigue happens that taxes them in a way that will drive them to adapt. It's not that, oh, I just got and I developed this peripheral fatigue or this central fatigue, right? And that it's the hydrogen ions that drive an adaptation. It's the lack of ability to have acetylcholine that drives an adaptation. It's really the consequences of how hard I have to work and push cardiovascular, the respiratory, the metabolic systems to get to that place. So generally, the stimulus for aerobic training is going to be related to something that we call overload. Okay, overload. So any of you guys that had an undergraduate background in exercise physiology probably have learned about something called the FIT principle and something called progression, regularity, overload, and specificity. Okay, but the idea, the stimulus that we need is an overload stimulus. So that means that we are going to make you do more or work harder than what you're accustomed to. Okay, so if Elise is used to or accustomed to running a mile, we're going to have her run a mile and a half. And that's going to make her cardiovascular system, her respiratory system, her metabolic system, and other things in her muscles work more than what they're accustomed to do. Or she can still run a mile, but she's got to run a mile faster. You're used to running a mile in 10 minutes, running it 9 minutes. So again, we're making you do more work or taxing your physiological systems more than what they're accustomed to. Okay? That's the idea of overload. Without overload, we get no adaptations. Okay? The other piece of this is an idea called specificity. What specificity tells us is if you run, guess what you're going to get better at doing stuff? Running. If you bike, guess what you're going to get better at doing? Only if you're very unfit. Only if you're very unfit. Okay? When you ride the bike, you get better at biking. It's just the way it goes. Okay? So, and that the adaptations that take place will occur in the specific systems that are being overloaded by whatever it is that you're doing. So, if you're making your cardiovascular system work harder, it will adapt. Okay? If you're making your mitochondrial work harder, they may adapt. Okay? So the adaptations are very specific to what it is and the systems that are being used. Okay? So if we want to overload with aerobic training, we can do it in one of two ways. You have to make the work you're doing during a bout of exercise go up. And so this is a very kind of loose way of approaching all of this. Some people would say that this is training volume or whatever. Like, I'm not going to get caught up in the semantics of it. But, right, the intensity or the percentage of VO2 max at which you're exercising is intensity. The duration, how long are you going, okay? And then the frequency, how many days per week are you doing it? So in a given week, I go 4 days a week for 30 minutes at 60% of my VO2 max. That's my work. If that's what I'm used to doing, I can keep 30 minutes, 4 days a week, and I can go at a higher intensity. Okay? I can keep my intensity and go for a longer period of time. I can keep both of these and I can go a fifth day rather than a fourth day. So all I've got to do is I can increase any of these things and my total work or my total training volume goes up. That should be at least initially sufficient to overload, and then I will get adaptation. Does that make sense? It's the amount of work that you're doing that leads to the fatigue. Right? That leads to the fatigue. That's where all this is going to come. Work goes up, and intensity goes up, or duration goes up, or the number of days per week, kind of day over day goes up, you're likely to get more fatigue during a bout. That's going to be the thing. Your systems will then adapt in an effort to limit the fatigue the next time you do the exact same thing. If you're used to running for an hour at 7 miles an hour, and then you go and you run for an hour at 8 miles an hour, good luck to you. That's going to be a stimulus that's going to try to drive the metabolic systems, the cardiovascular systems, the respiratory systems to limit the fatigue the next time you have to try to run. So what of these things is the most important? Before we get into what actually changes in my house, what of those things are the most important? If you had to pick something, okay, to do, intensity is probably the single most important. For most people, maybe not some of you, you're probably fit enough, but for most people, you need to go and exercise when you do aerobic exercise at least 50% of your VO2 max in order to drive adaptations. If you're pretty fit, it might need to be at 65 or 70% of your VO2 max. Right? So what we know is that in general, just cranking up intensity is generally going to be good for you, okay, from an improving VO2 max. And I should say this right now, okay? What you guys are going to see here is what we know that makes VO2 max go up. We're not specifically talking about like 1 mile run time or 5K biking time trial time or actual measures of performance. We're talking about VO2 max, right? Because that's the easier. The actual performance things require some additional stuff. Okay. So you can make the intensity go up by running faster, running up a hill, or if you're on a bike, by increasing the power output on the bike, making it, increasing the pedal frequency or something like that. All of a sudden, I'm overcome with tiredness, which is not fatigue. There is a distinction. What's that? I'm okay. All right, so if intensity is the most important, I don't want to say that duration is the second most important, but it probably is the second most important, rather than frequency. Okay, so at a given intensity, if you will go longer, your VO2 max will probably go faster. Okay, this effect tends to plateau around 40 minutes of exercise. Okay, you see no further increases in VO2 max if you go for an hour or if you go for 90 minutes or something like that. Okay? Tends to plateau. So 40 is better than 30, 30 is better than 20 at the same percentage of VO2 max. Same absolute intensity. Longer up till then, it's better. I think I know what your question is going to be, Matt, but ask it anyway.
Which of these would induce the most fatigue? Would it be in the same order? This fatigue is related to increasing VO2
and the frequency thing, you get to rest in between days, and so there's a little bit of a knock-on effect up to a point, so you may get a little bit more benefit out of your back couple of days, doing 4 days or 2, but yeah. And so then frequency-wise, at the same intensity, at the same duration, you can increase VO2 max up to about 5 days a week of exercise. The 6th and the 7th day don't get you any further benefits. Okay? Please hear what I said. Those of you that are athletes, don't go tell your coach that Dr. Black said you don't need to train more than 40 minutes and you don't need to train more than 5 days per week. Even though that might be optimal, okay? if you're going to do an event of some kind that lasts longer than 40 minutes, you're going to play a soccer match, you're going to run a marathon, I need to implore you that only doing this, your VO2 max won't go up any further, but how you feel after that 40 minutes, in that other hour or whatever you're doing after all of that, how you feel there will be dramatically different, okay, if you've actually practiced for that duration. Okay? I am notoriously giving distance runners a hard time because I think they run too far too often, right? Our cross-country team runs like 100 miles a week. They'll have some days where they'll run like twice or 3 times in a day. You know what the race distance? They'll go run 10 miles on a week. You know what the race distance is? 10 kilometers. People that are really good at that run that in, like, I don't know, somewhere between 30 and 35 minutes or something. Right? Maybe a little lower than that even. Okay. So why would you want to go run 10 miles and go run for an hour and a half slowly? Right? How is that specific to what you do on your race day? Okay? I think they run too much. That's just me. Though I did read a thing yesterday or the night before. I forgot what it was in. I meant to print it off and bring it for you guys, or at least get the thing. It was an article about Eliud Kipchoge, who's the world record marathon runner. And the guy had gone to Africa and was like hanging out at his training camp with him, talking about things, how much they run. And so he runs like 5 days a week. He takes a couple of days off. He doesn't run hard on all 5 of those days. But they do run multiple times a day. So I found that fascinating. So that's kind of where we are. Okay. This is the necessary stimulus. You need to be doing this. The other thing to keep in mind, as you adapt, doing the same thing begins to be easier. It causes less fatigue. So guess what you have to do? You got to make it hard again. Right? That's called progression. It's called progression. You want to evoke something called progressive overload. You do something, it's hard. You keep it while it's hard for a few training sessions, and then you're going to begin to adapt. It becomes easier. Then you need to change it and run faster or run longer, okay? Or do another day a week to make it overload again. And then you will adapt to that. Then you got to go and make it more difficult again and again and again and again, okay? The biggest mistake that most people make when they train is they don't get enough intensity. Okay? They don't go fast enough if they run. They don't go at a high enough power output when they bike, or they don't ride at a fast enough speed when they bike. And they don't adequately get progression. They've been doing the same thing for months and months and months. And they wonder why they're not getting better. So that's the thing. For me to get better, I got to go chase that girl that's in, that sounds bad. There's a girl that is in Elise's or maybe in somebody else's individual fitness class at the same time as Elise's class on Tuesdays and Thursdays. She's in Gabe's class, and she freaking kills it on the track.
She signs out and then goes up and keeps
And
running.
yeah. She runs very fast and like runs like the whole time, and I'm up there doing like, a mile and a half, just freaking sucking wind. And she's just, I need to go and let her try to set the pace for me, because that would make me get better. Okay. So, but that's hard. It's hard to do it all by yourself. It's hard to keep pushing these things because it sucks. It's uncomfortable to do all. Okay. All right. So let's talk about what it is that changes. Okay. I'm going to break the things that change down into things that happen in the muscle and in the metabolic systems versus things that happen in the cardiovascular system versus things that might happen, which is almost none that happen in the pulmonary systems. Okay. So if we look at muscle metabolic adaptations, if you look at anaerobic metabolic pathways, there are almost no changes whatsoever that occur, which should make sense, right? It should make sense. We're not, I mean, we are taxing the anaerobic systems, but there's just not a lot that can change. Okay? The big thing that's going to really happen in this area is, you may say, the change in lactate threshold, which I would say is nothing to do with the glycolytic pathways. It's all to do with the aerobic pathways. And you're going to see a big increase in the hexokinase enzyme, which is, that first step in glycolysis. But again, I think that's going to really function to push aerobic metabolism rather than it being kind of an actual anaerobic adaptation. Okay. Most of the changes that we see are going to happen, right, after we've made pyruvate. That part of the metabolic cell. Okay. So that means where are they going to take place? In the mitochondria, says the guy that studies mitochondria. Very good guess. Okay. For the most part, the metabolic adaptations are all going to take place in the mitochondria. And in the mitochondria is even sometimes a bit of a misnomer. It's just that there will be more mitochondria. It's going to happen. Okay. So if you look at glycolytic changes, you may, in some studies, we see a little bit of a change in PFK. It's really kind of mixed, so it's not like we magically like speed up or slow down PFK. We don't really see a lot of changes in LDH. There may be a little bit of a decrease or a shift from the muscle to the heart isozyme, especially in 2X fibers, but a lot of that is driven by the fact that you just don't have any more 2X fibers. Your 2X fibers all become 2As. Okay? Big increase in hexokinase. Big increase there. That's going to function to lead to greater use of glucose coming out of the blood, trapping that in our cells so that we don't have to use muscle glycogen as our carbohydrate. The functional adaptations that you will see from this, okay? How are these changes, especially maybe the hexokinase one, how are they going to function to limit fatigue, which is our goal? It spares muscle glycogen because we're using more blood glucose, or we're using glucose that has come out of liver glycogen. And we're probably going to produce a little bit less lactate if we can shift away from 2X fibers and a little bit of those changes, right? But it mostly is going to spare muscle glycogen. When you lose muscle glycogen, that causes central fatigue. So please, again, here's a peripheral adaptation that limits central fatigue. The big thing that happens in the muscle is you get more mitochondria and you get bigger mitochondria. Right? More mitochondria, bigger mitochondria. In some instances, depending upon where you're starting, you may be able to double mitochondrial content. Right? Double. You will make new ones. We will talk very briefly about kind of the pathways that drive some of that, and the ones that you have are going to get bigger. Having more mitochondria increases the number of Krebs cycle enzymes and Krebs cycle substrates, and it increases the number of electron transport chain components. I'm sorry? The ones you have function, that's 100% sure. If I have more Krebs cycle enzymes and I have more electron transport chain components, what this leads me to be able to do is there's a greater chance or a greater opportunity for every pyruvate molecule that gets to the end of glycolysis to go into a mitochondria to be used in aerobic metabolism. Make a bunch of ATP. And that will then prevent that pyruvate from having to go into lactic acid. Okay? You've got twice as many mitochondria, you've got twice the likelihood that that pyruvate molecule can go into one. Okay? So you can increase your ability to handle that pyruvate. Additionally, by having more mitochondria, I can also have a greater ability to put fat, metabolize fat to get energy. Remember that what we're trying to get to here is a sufficient amount of ATP so that we can limit fatigue. Okay? We need to be able to run the sodium potassium pumps on the sarcolemma. We need to be able to run the sodium potassium pumps to maintain T-tubule excitability. We need to be able to supply ATP to the calcium ATPase so that we can resequester calcium in the cytoplasmic reticulum. We need ATP to be able to run the myosin ATPase enzyme so that we can repack and hydrolyze ATP and repack the myosin heads. Right? So we need energy to get force. We don't care where the energy comes from. We just want to make sure that we're using it in the aerobic pathways or getting as much of it from the aerobic pathways as we can. So by doubling this, that means we can bring in and use more fat and we can send more of the pyruvate there. So we're going to make energy without having to make lactic acid. Okay? That's going to be good. I can do more of that, then I can use more oxygen. Voila, my VO2 max goes up. Some of you may ask, and it would be a wonderful thing, I don't think we can do it. Is there a way to artificially just inject you with more mitochondria? Kind of like blood doping, can you just mitochondrial? I don't think that we can. But if we can, I want in on your business. That's all I'm saying.
Would you inject the cells or like,
Satellite cells.
yeah?
So the mitochondria don't really come from satellite cells. So the mitochondria have their own set of DNA because they used to be parasites, basically.
But how would you inject it? Would satellite cells be the transporting mechanism of it? Or?
So the most likely scenario would be biomedical engineers. Ears are going to perk up. If we were at Stanford, right, we'd just do this and then we'd tell a bunch of lies and sell things and then get sued for our pants off, right? I can run anything from one drop of blood. I'm just talking about Theranos, right? You guys seen the documentary about that? Anyway, so I totally lost my train of thought trying to make a Theranos joke, which, you know, super niche joke for my biomedical engineers. The most likely thing, Christina, would not be to give you mitochondria. The most likely thing to do would be to give you something that would stimulate mitochondrial biogenesis. I need to find a way to stimulate something called PGC1 alpha so that you will then stimulate sort of mitochondrial DNA transcription. Does that seem reasonable, gang?
Yeah. Oh, and it's so very special.
Yeah.
But I don't know how to do
I don't do it in humans, but we can do it in mice. We probably want to infect you with a virus that had, that had some sort of the sequence for the mitochondrial DNA in a vector or something, and then get it to overexpress. Oh yeah, that's how we get things in. We just infect you with a virus. It wouldn't like do anything to you. You just make more of all of this, or we turn on the expression of those things. Very, very commonly done in cell lines and those kinds of things. So that would be my guess. I don't really know. I don't know if we gave you somebody else's mitochondria, like would your immune system attack them? Would it recognize them as foreign? If they're already in a cell, I don't know what like the glycosylation like on the outside would look like. I don't really know. But if we could test you, we could know if all of your mitochondria were from the same place. Right? If you were a doper, we could figure it out if we could get a muscle sample. Twins. We were talking about twins this morning in my undergrad class. So we have a girl that's on the track team, and like they have twins, identical twins on the track team. So I did not know that. So then I have another girl in the class who's a cheerleader, and one of her roommates is an identical twin, but the second twin doesn't live with them. So one of them made cheer and the other one didn't make cheer. Like, ooh, that's tough. So, right, nature versus nurture, right there. Pardon? I know, right? I know. Okay. Yes, Josiah.
So when we have, since we have the greater ability to have less fat, would that also mean that it would shift the curve more to the right of only using the fat metabolism at 65% of the VO2 max? So would you That doesn't change.
It goes the other way. It shifts left. You're going to use more fat even sooner. Like you use more fat at rest in that. Okay. So that's it. But you're thinking about it in the right way. It definitely shifts everything. So it would go for you that way. Left. So it's one of the benefits of being aerobically trained. You metabolize more fat at any given exercise intensity or any given amount of fat that you have. Okay. So you guys are probably wondering, Dr. Black, how do we know if it doubles or what else is going on in the midst of all of this? Here are some of the original data. I don't know if it's the very first data, but these are from John Hawazi's lab, Washington University in St. Louis. Really pioneered the vast majority of these things with his buddy Vince Saltine. And these are rats. They did 12 weeks of running on a little flywheel, 5 days a week, 10 to 30-minute bouts. They progressively increased the speed. If they're increasing the speed, then they actually had them on a treadmill. You guys ever seen a rat treadmill? You know how they get the rats to run on the treadmill? Forcibly. They put what is basically electric fence at the back of it. And if the rat refuses to run, it gets fucking shocked. Some rats are real jackasses. They do like, I'm not going to run, screw you, I'm just going to sit there. And they just get shocked. I've seen a video. It's truly awful and heinous. Please don't come after us, PETA. I've never done it. Well, I can't be an animal research, but they provide them a little incentive with all of that. So with 12 weeks, what you can see, right, here is cytochrome oxidase, succinate oxidase, okay? And they've got it from the gastroc and soleus, and you will note that basically these are going to be enzymes. Krebs cycle enzyme, cytochrome oxidase is going to be the thing that's going to go out of the electron transport chain. And so you will note that those things go up very, very dramatically in the midst of all of this. Here is mitochondrial protein content. So they, of course, sacrificed the rats and ground up their muscles and measured how much mitochondrial protein there was per gram of actual muscle weight. And you will note that it was up about 1.5 times or thereabouts there. So these very, very kind of initial significant changes in mitochondria. Okay? And much of this has now been repeated in humans. Okay. So this, of course, I'm going to guess is going to raise the question of how are new mitochondria formed, and then what is it about exercise that stimulates their formation? Okay. So as I mentioned a minute ago, mitochondria have their own DNA. Okay, but they also require genes from the host muscle fibers, so from the host nucleus. We need all of those things together to be able to actually synthesize new mitochondria. Okay. So one of the places that plays a role, and it plays a role in a bunch of things, but it's kind of a metabolic sensor in some ways, if you will, is a thing called peroxisome proliferator activated receptor gamma coactivator, which is called PGC1 alpha. Okay? PGC1 alpha. This is an important kind of coordinator of mitochondrial biogenesis. What you can see, and this is going to seem weird, I just like these data. I thought they were very kind of nice, but these things were published in people that were diabetics. They were training diabetics. I mean, it doesn't matter, their muscles just like ours. So this is from 2003. But here's the amount of PGC1 alpha messenger RNA in muscle cells per, they're normalizing it to beta actin messenger RNA, which is just a way the beta actin should be relatively constant. This is the way to kind of normalize this if there's changes in fiber sizes and those things. So pre-training to post-training, right? Almost a 200% increase, right? Here's PGC1 alpha protein content in these people. This is not just messenger RNA. So we've got messenger RNA. Here we've also got protein content, and it's in type 1 fibers, 2As and 2Xs. And what you will really note is the big, big explosion is going to take place. So these two are different than 2Xs. And then here and here, they've all gone up afterwards. But the really big explosion is going to take place in 2A fibers. So you guys have lots and lots of 2A fibers. You actually end up with more because you turn your 2Xs into 2As after running. or biking or something, but these are the ones that have a giant capacity to increase the mitochondria. So this is from Physiological Reviews from 2008. And part of what we're seeing is I just want you all to appreciate, here's our mitochondria. Here are some of the signals. There's a bunch of signals that are going to be required, okay, to drive mitochondrial DNA transcription, right? And some other things that are going to go on. They're going to drive from inside the nucleus. They're going to drive translation of additional mitochondrial proteins. But you can look at a lot of these things, okay, and see that PGC1 alpha is one of the kind of common regulators of all of this stuff that happens downstream, okay? And what you will note is that when you deprive yourself of energy, either via starvation or especially during exercise, it activates AMP kinase, and AMP kinase is probably going to activate PGC1 alpha, okay? But then there are a whole bunch of other things like cyclic AMP, signaling to PKA, things from exercise, maybe some effects of calcium, calmodulin and calcineurin that they may actually function to inhibit PGC1 alpha. So weirdly, PGC1 alpha is useful for mitochondrial biogenesis, but also for muscle hypertrophy. And so we're trying to work out the balance of kind of metabolic activation versus calcium activation and some other kinds of things is probably beyond my scope. I should probably go ask Gabe's boss what we should be teaching about all of this. But I just want you to know that PGC1 alpha is important. Okay, this is one of the kind of key regulators. Okay. And then of course there's all of these different sort of downstream signals that are going to come from PGC1 alpha. They're going to lead to kind of the formation of these. Okay, let's call it quits there for today. We'll do some more on Monday.